In this video, we're going to look at how to find orders from experimental results. And this table here is called an initial rates table. Orders of a reaction must be found experimentally. They cannot be found through a balanced chemical equation. This is a common misconception. The first step in a question like this is to find two experiments where the concentration of one of the reactants remains constant while the concentration of the other reactant changes. So if I want to find the order with respect to oxygen, I'm going to look at experiments 1 and 2 because the concentration of the other reactant is constant. And that means whatever is happening to the rate of reaction here is just from the contribution of the oxygen. So if I have a look at these numbers then, the oxygen, its concentration is increasing by a factor of 3, and then we want to find out what the rate is doing. So if I was going to do that on a calculator, I'd do this number over this number to get 3. And here I'm going to do the same thing. So I'm going to do the row 2 value over the row 1 value. So 5.46 times 10 to the minus 6 over 1.82 times 10 to the minus 6. And we also get 3. So when we increase the concentration of the oxygen by 3, the rate also increases by a factor of 3. So this means it's saying that the concentration of the oxygen is directly proportional to the rate. That is first order with respect to WRT, the oxygen concentration. Let's find the order with respect to this one then. So again, we want two experiments where the concentration of one reactant is constant and the concentration of the reactant whose order we're trying to find is changing. So we're going to use experiments 1 and 3 this time. And we can see that if we do this number over this number, the concentration is increasing by a factor of 2. Let's see what's happening to the rate. So we're going to do this number over this number. And we'll see that the rate is increasing by a factor of 4. So here, the rate is directly proportional to the concentration squared. And this is second order. Now let's write a rate equation for this reaction. So we start rate equations with rate equals K. It has to be a lowercase k, that is the rate constant. And we've got the oxygen, which was first order. So square brackets mean concentration of the thing inside. We could write a 1 for first order, but we don't really need to. We don't need to write the 1. And all these terms are times together. Times by the concentration of the other reactant raised to the power 2 because it's second order. So that is the rate equation which we've got from these experimental results. So now we can take this further and we can calculate the rate constant K by rearranging this equation. And we can choose the values from any one of these experiments here. So I'm just going to pick this first row. And remember to square this value because you have a squared here for the second order reactant. And we should come out with a value of 1820 for the rate constant. We can also get units for this rate constant. And what we do to get the units is plug in the units of the terms in this equation. So units of rate are moles per decimeter cubed per second, And then units of concentration are moles per decimeter cubed. Remember the squared for the second order term. Next we cancel out what's the same on top and bottom, and we're left with this. We can times out this bracket here. And the last step is to move the things that are on the bottom to the top. We want to move everything to the top line. And when we change sides, going from bottom to top, we change signs. So this moles plus 2, or this moles squared at the bottom, is going to become moles minus 2 when it moves to the top. And this dm minus 6 will become a dm plus 6. And seconds to the minus 1, that's already on the top line. So that stays as it is. So our final answer for K is 1820, and its units are these. And the units will depend on how many concentration terms we have for that particular reaction and their orders.